The Pythagorean theorem is considered by many as one of the best known and most useful theorems in mathematics. This is attributed to the Pythagoreans, who proved this theorem about 2500 years ago, which was led by the Greek mathematician and philosopher Pythagoras. The Pythagorean theorem is used when the length of one side of a right triangle is unknown and the lengths of the two other sides are given. The theorem states that in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the two legs. In symbols, we have the square of the hypotenuse is equal to the sum of the squares of the two legs. Applying the Pythagorean theorem in right triangle USL, we have the hypotenuse is segment UL. We square segment UL, that is equal to one of the legs is segment SL. We square segment SL. And the other leg is segment US. We also square segment US. So that is the square of segment UL is equal to the sum of the squares of the two legs, which are segment SL and segment US. Always take note that the Pythagorean theorem is just applicable for right triangles. It is designed for right triangles only because this is the only kind of triangle with two legs and a hypotenuse. Let's try to find the length of the unknown side of right triangle MSU given the lengths of its two legs, which are 6 units long and 8 units long. By Pythagorean theorem, we have the square of the hypotenuse is equal to the sum of the squares of the two legs. In the figure, the hypotenuse is segment MU. So we square segment MU, and that is equal to one of the legs is segment SM. We square segment SM, and the other leg is segment US. So we add this square of segment US. Your segment MU is the unknown, so we just need to copy the square of segment MU, and that is equal to segment SM is 6, we square 6, and segment US is 8, so we add this square of 8. We copy once again square of segment MU, and that is equal to the square of 6 is 36, the square of 8 is 64. Adding 36 and 64, our sum would be 100. In order for us to solve for segment MU, all we need to do is to extract the square roots of both sides of the equation. We have the square root of the square of segment MU is segment MU, and the square root of 100 is positive negative 10. Since we are just talking about length here, all we need to get is the positive square root since there is no negative length. So the length of segment MU is 10 units. This time, we solve for the length of segment LP in right triangle LPT given the length of the hypotenuse, which is 11 units long, and the length of one of its legs, which is 9 units long. By Pythagorean theorem, we have the square of the hypotenuse is equal to the sum of the squares of the two legs. The hypotenuse in the figure is segment PL, and the two legs are segments LP and TP. We then have the square of segment TL, the hypotenuse, is equal to the sum of the squares of the two legs, which are segment LP and segment TP. By substitution, we can solve for the length of segment LP. Segment PL is 11 units long, and segment LP is the unknown. Then segment TP is 9 units long. The square of 11 is 121 equals the square of segment LP plus the square of 9 is 81. By addition property of equality or by transposition, all we need to do is to copy 121. Then 81 from the right will be transferred to the left. It becomes negative 81. That is equal to the square of segment LP. The difference of 121 and 81 is 40 equals the square of segment LP. Extracting the square roots of both sides of the equation now, we have the square root of the square of segment LP is equal to segment LP. And since 40 is not a perfect square number, all we need to do is to think of the highest perfect square factor of 40, and that is 4. 40 divided by 4 is 10. Therefore, we have the square root of 4 times 10. Square root of 4 is 2, and the square root of 10 is still square root of 10. That leads us to the length of segment LP, which is 2 square root of 10 units. We now solve for the length of segment AT in right triangle SAT, given the length of the hypotenuse, which is 10 units long, and the length of one of its legs, which is 2 square root of 10 units long. By Pythagorean theorem, we have the square of the hypotenuse equals the sum of the squares of the two legs. The hypotenuse in the figure is segment PS, and the two legs are segment AT and segment SA. The square of segment PS then is equal to the square of segment AT plus the square of segment SA. We can solve for the length of segment AT by substituting the given to our formula. Segment TS, based on the given, is 10 units long, equals segment AT is the unknown, and segment SA is 2 square root of 10. The square of 10 is 100, equals the square of segment AT, and the square of 2 is 4, and the square root of 10 is 10. That leads us to 4 times 10. The square of 2 square root of 10 would mean 4 times 10. We simplify, we have 100 equals the square of segment AT. 4 times 10 is 40. This time, we perform transposition or the addition property of equality. We have copy 100, then 40 from the right will be transferred to the left. It becomes negative 40, and that's equal to the square of segment AT. The difference of 140 is 60, equals the square of segment AT. Extracting the square roots of both sides of the equation, we have the square root of segment AT is equal to segment AT. And since 60 is not a perfect square number, if we try to think of the highest perfect square factor of 60, that is 4. 60 divided by 4 is 15. We then have square root of 4 times 15. Square root of 4 is 2, and square root of 15 is still square root of 15. So, the length of segment AT now would be 2 square root of 15 units. We now solve for the length of segment MO in right triangle NMO, given the length of the hypotenuse, which is 15 units, and the length of one of its legs, which is 6 square root of 5. The hypotenuse in the figure is segment NO or segment ON, and the two legs are segment MO and segment MN. So the square of segment ON, the hypotenuse, is equal to the sum of the squares of the two legs, which are segment MO and segment MN. By substitution, we have segment ON is 15 units long, segment MO is the unknown, segment MN is 6 square root of 5 units long. The square of 15 is 225 equals the square of segment MO. The square of 6 is 36, and the square of square root of 5 is 5. That leads us to 36 times 5. So we copy now 225 equals the square of segment MO. Then 36 times 5 is 180. By addition property of equality or by transposition, we have to copy 225. Then 180 from the right will be transferred to the left, it becomes negative 180, and that's equal to the square of segment MO. The difference of 225 and the 180 is 45, and that's equal to the square of segment MO. Extracting the square roots of both sides of the equation, we have the square root of the square of segment MO is segment MO. That's equal to the square root of 45. Since 45 is not a perfect square number, then we think of the highest perfect square factor of 45. That is actually 9. So 45 divided by 9 is equal to 5. That's why we have square root of 9 times 5. So square root of 9 now is equal to 3, and square root of 5 is equal to the square root of 5. That leads us to the length of segment MO, which is equal to 3 square root of 5 units. Triangle CAS is a right triangle. Find the length of segment CS if angle A is 90 degrees, segment CA is 3 square root of 6, and segment SA is 3 units long. We need first to illustrate the given problem in order for us to easily solve it. We have here a right triangle, and it was stated in the problem that angle A is a right angle. Since here is the right angle, we can therefore say that the vertex where the right angle lies will be point A. So we name this vertex as point A. As you can see also here, segment CA is longer than segment SA since 3 square root of 6 is longer than 3. So we have to name then this vertex at the bottom as point C, which now leads us to have segment AC as 3 square root of 6. The third vertex of this triangle now would be named as point S. Then segment AS now would be 3 units long. So by Pythagorean Theorem, we can solve for the length of the hypotenuse, which is segment CS. That is, the square of the hypotenuse is equal to the sum of the squares of the two legs. We then have the square of segment CS, the hypotenuse, is equal to the sum of the squares of the two legs, which are segment SA and segment CA. Your segment CS is the unknown, so we copy square of segment CS equals segment SA is 3 units long, and segment CA is 3 square root of 6 units long. So the square of segment CS is equal to the square of 3 is 9, the square of 3 is 9, and the square root of 6 is 6. That leads us to have 9 times 6. We have the square of segment CS is equal to 9 plus 9 times 6 is 54. So we have the square of segment CS now is equal to 63. Extracting the square roots of both sides of the equation now, square root of the square of segment CS is segment CS. Since 63 is not a perfect square number, we need to think of a perfect square factor, the highest perfect square factor of 63, in order for us to simplify it. And that is 9. 63 divided by 9 is 7. So our factors would be 9 and 7. The square root of 9 now would be 3, and the square root of 7 is still the square root of 7. And then we now have the answer for the length of segment CS as 3 square root of 7 units. So the length of segment CS, the hypotenuse of right triangle CAS, is 3 square root of 7 units.